Hi everyone, welcome to Digital Futures Young Series live session. I'm Sinan Mustafavi, joining from Delft in Netherlands, moderating this session on behalf of Digital Futures. This session is joined by Digital Futures Young Committee, organizers, and Neil Leach. Today is the third session of Young Series on robotic fabrication, which we have received through our open call. And for today, we have a very fascinating lineup of presentations by speakers joining us from all over the world. This session will be live streamed on YouTube and Bilibili, where you can leave your comments and questions. And we usually try to address all of them during the panel discussion after seeing all the presentations. For updates about upcoming weekly events, you may visit our website, digitalfutures.org, where you can find the links to our archive, as well as links to Digital Futures social media. We also would like to invite you, our presenters and audiences, to join our active Discord channel. Here we are going to share the link to the chat box of YouTube and Bilibili, and we would be more than happy if you join and contribute to the interesting discussions among our growing community on Discord. In our weekly sessions, which happen every Saturday, same time, in addition to Young Series presentations through the open calls, we have 3 other types of events, which are talks by Digital Futures instructors, keynotes, and special events. To name a few of upcoming special events, next week, we have a very interesting session on Africa on the 21st of October, where we invite you all to join. In the meantime, we are planning other special events such as space architecture and Amazon. Last but not least, before we move to the next thematic subject, an open call, which will be on AR, VR, and game. We will have our keynote session on robotic fabrication in 2 weeks, right after the Africa session. So for those who are interested in robotic fabrication, please do stay tuned, as we have a very interesting list of invited speakers to be followed by a panel discussion on the 31st of October on robotic fabrication. To start with today's presentations, we invite the first speaker, Rasha Alshami, to share her screen. Rasha is an architect, researcher, and roboticist at the Architectural Association School AA London, where she is a member of the Digital Prototyping Lab. She has previously worked at Zaha Hadid Architects. She has also finished her master's degree at the University of Stuttgart in the iTech program, where she has been involved in multiple projects such as Buga Fiber Pavilion. She has recently started working as an architect and robotic programmer at Lilium, an aviation company based in Munich in Germany. Rasha, you may start.
Thank you, Sinan, for the introduction. I hope you can see my screen. I'm just confirming.
Yes.
You are muted now. Rasha, you're muted.
Rasha, can you please unmute?
Yes. Is this okay? Great.
Yeah, you may.
And my screen, you can see my screen, right? Okay, so thank you for the introduction, and hello to everyone who's tuned in. Thank you also for inviting me to be part of this intellectual robotic talk and present my work. So let me see, because it's, okay. So today I will be presenting one of my collaborative robotic research studies that I have worked on while I was obtaining my master's degree in Stuttgart in the iTech program. The topic of the presentation is focused on digital operations and building operations through implementation of neural network approach and machine learning to pick up on traditional methods of construction techniques such as dry stack stones. I thought I'd start my presentation with this very fun short video summarizing what I will be presenting before diving in the details of the actual presentation. So it's important to mention from early beginning that this research does not focus on creating designs nor robotic end effectors that are of high-end quality, but instead it focuses on making an automated robotic output through implementing neural network approaches for learned building operations. Honestly, I really believe that this could revolutionize the use of robotic construction in hazardous areas or areas where humans can't reach or work in, and perhaps give birth to a new type of architecture. So moving on, allow me to start by saying that, as you all know, we have been writing about robotic arms, seeing them in movies and program them to do repetitive tasks like welding and milling, but not until lately, we have started seeing them employed by architects and designers, which opened up a new door for fascinating ideas and outputs, making this what's so-called the age of digitization, virtualization, and automation. So as an architect, researcher, and robotic programmer, my interest in robotic arms increased the minute I saw the fascinating potentials of using these robots for rapid production and making these novel structures, especially when I was assisting on fabricating the Buga Fiber Pavilion during my studies at ICD and ITKE. And it most certainly showed me a unified process between designing and building. And this really made me curious to see how can I make robots think, build, and operate on their own, and if that even is possible. So the answer is absolutely yes, that's possible, but we need to kind of take baby steps here. So I started thinking of what building technique can I transfer to a robot using off-the-shelf materials, then how can I make that technique a machine-learned operation, allowing the robot to learn? So I found out that dry stacked stones is actually considered one of the simplest methods of construction for humans, but it's physically exhausting and it requires humans to build cognitive learning skills over time. And so this made me again think, how can this method or process be transferred now to a robot, which will the robot again recognize these different shape inputs and arrange them in a way? And what if it can like make this like stable wall and also learn over time from its failures? So to understand a bit more how dry stacked stone work and how this technique works, it's basically kind of like where the builder checks if a shape fits, one of these stones fits in the configuration or not. And of course, it's quite tricky to explain to a robot this process. So to find the answer to this research, I tend to refer to nature. Funny enough, the Trichopetrus caddis larva building behavior is related in that sense, because these creatures have the ability to scan objects around their environment and test the validity of these objects that they have picked in an attempt to build a temporary aquatic cocoon. And so as a researcher, I find such examples relatively intriguing and solution-oriented. So this behavior now can be actually applied to build this robotic information in a similar way. So if we look at these data inputs at some scattered objects around and we process them in a way, we can have them reincarnated into a new physical output. And so from here, I think like a behavior could be then taken a step forward and embedded into a robotic arm through a more detailed workflow by creating a machine learned tool utilizing computational based engine. And then this engine is able to create a database, or what's so-called in this case, a library of inputs or a brain from these scanned objects. And then the robot arm can recognize them and stack them based on principles that are developed and enhanced over time by this computational engine itself. And then it would construct a stable wall. So the workflow was actually developed in three main environments or three main softwares. One is Grasshopper, the second is Unity, and then KUKA. In Grasshopper, we have a set of cloud points that are imported from scanning process using the Connect, and then the cloud points are trained for recognition. A mesh is constructed from the cloud points and then sent to Unity 3D for stacking and learning. After the stacking simulation is completed, the positioning of the selected simulated stacked items are sent back to Grasshopper and then communicated to the robotic arm through the KUKA server, and then it would stack in real time. So for the purposes of this research, a multi-end effector was built to provide this required functions for scanning and grabbing. And as I mentioned earlier, the end effector is not of an high-end end effector. It doesn't focus on, this research does not focus on creating complex grippers, but rather focuses on testing and building a machine-learned engine to test the ability if the robot actually can recognize and build and also learn. However, this is just a proposal that we thought that it could be looking nice, so it can do the job for us. So to dive in a bit more on how the engine was built, this diagram simply presents how the library or the brain is constructed. So as you can see, there's a library that is made of folders. Each folder contains a list of subfolders representing faces, and then each item face is derived from a set of trained cloud points that are scanned from the physical object. So to understand a bit what training set is and what machine learning is, the way machine learning and deep learning works is that you have a data set first that are extracted in vectors from its characteristics, and then this extracted data set is trained where an algorithm starts looking for patterns between the data set. So to simplify it a bit more, is like basically teaching a child what an apple is and how it looks, and then when the child will go and see a different apple color or a bit distorted apple, it will always recognize it as an apple. So that's kind of a simplified way of how this visual learning works. So I also would like to mention that we used a Crow plugin developed by Benjamin Philbrick for this engine, for the machine learning process. So to follow up, basically the engine implements this neural network approach through training and saving the scan data in a computational engine. And then the scanning process is very important because what it does, it allows to build accurate information about the object and creates a 3D mesh from the scanned results. So the more scanning there is and the more training it is, the more accurate that object is. So the Connect scanner basically was used and attached to the robot, and then there was a turntable that helped in scanning all the sides of the object. In this case, it was a stone. And also there were stacking principles that were embedded in Unity 3D to allow the engine to experiment and learn from different results of stacking and only export data if the wall is stable. If not, it will go back and stack again until it's stable. So then 3D meshes of these scanned stones are imported into Unity, as I mentioned, and then there's a stacking simulation that started running. And then in this simulation, there are machine learned principles that are applied as well. And then the engine keeps on experimenting and learning until it achieves a stacked wall. So in case a secured wall has been reached in the simulation, the selected rocks of their identification and proposed location are sent back to Grasshopper. And then in Grasshopper, there's a sorting process of this imported information that takes place, allowing the robot to search and stack the first layer of the wall, then the second, then the third, until this is completed. And so if we go back to the machine learning algorithm again, we can see that the searching for the objects now will work in a similar way, where we are testing the set that we have taught the robot. So basically, by utilizing this machine learning algorithm, the algorithm generates now a model that can provide the new data set that will cluster the new elements, basically where the machine have never seen these items before, but it learned over time what they look like. And then it will go into that they came from the training phase, and then it will go and recognize these objects. And so the robot now will start look for these items that are required to be allocated. And then in case the scanning process did not work in the first phase, a second layer of scanning will take place again. But I can assure you that the scanning process have worked all the time. and it was very correct. We also used very similar stone shapes and draw shapes on each face just for us to see if the robot can recognize with how much accuracy can it recognize these stones, and it was 98% correct. And so if an item has been found in the pile of these stones or objects, the robot arm switches to the gripper and then approaches the recognized item to grab it and place it in its corresponding computed location identified from the Unity simulation. And so basically here we are testing both methods in the Stuttgart robot lab, where we are scanning on the far left, and then the robot is actually looking for these items. And then once it recognizes one of the items that corresponds to that one in the simulation, it will go grab it and place it in its right location. As you can see, it's a very humble end effector, but again, it does the job. So it was perfect to actually check if this brain works, and it did. So to sum up this talk, even though that the designed engine proved its workability on a robotic arm scale, it would be really interesting to have a look on how we can introduce mobile robots into the system and create a more collaborative approach, allowing all types of robots to build and construct together, basically providing this like optimal construction scenario in hazardous areas like Mars, for example. So thank you all for tuning in, and I look forward to this discussion, and you can also reach me on any of these social platforms. Thank you.
Great, really interesting work, Rasha, sorry. I wonder if you have some questions from the audience. If not, maybe I ask a very short questions. It is really interesting to see how sort of monitoring the input data or the input material results into sort of informing the whole system in a way, introducing a feed forward to the whole, this systemic thinking that you have developed. I'm sure that we can come back to this topic later on when we see other presentations. But I'm also interested to know, how did you deal with the tolerances? Because the material that you are working with, it's a very rough material. And how did you deal with errors, or how did you sort of think about it?
Yeah, so that's actually a really great question. If you're referring to the materials itself and the tolerances, there were no tolerances. The Connect scanner was collecting data really quite well. And because of that, we were able to construct a really accurate 3D mesh from these point of clouds. However, the let's say this deviation that came out when we were constructing that simple, like stable items that were stacked together, the inaccuracy came from the end effector itself, because as you saw that there's like this balloon that has actually coffee in it, and that's where this inaccuracy came from. If we had a really good gripper, I think it would be quite accurate and there were no deviations at all.
Really interesting. Great. So I think I hope you could stay with us in the panel discussion. So for now, if there's no any other burning questions, we move to the next presentations. And we ask Ricardo Meyer from IAAC, Institute for Advanced Architecture of Catalonia, to share his screen. Ricardo is a fabrication expert and faculty at IAAC. He holds two master degree, one from Technical School of Architecture of Alcalá in Madrid, and a master degree in advanced architecture from IAAC Barcelona. Since his graduation in 2012, he is one of the 4 founders of Design Architectural Territories, who was awarded the first prize for the best young architects in Europe for their sustainable construction by Lafargue Hall Kim Foundation. So Ricardo, if you could start sharing your screen, it would be great. We don't hear you yet.
Now, can you listen? Can you listen me? Can you see my screen?
Yes. No, yes.
Perfect. Yeah. Well, so hello all. First, thanks to all the digital future organizers and team to having me here today. Well, today I'm talking about the work that we developed in IAAC in the last Global Summer School Intense Online workshop, named Design for Robotics Fabrication through Remote Control. First, Sina already mentioned it, but here I would like to show you quickly a mood board about me. I'm nowadays working in IAAC in the Advanced Architecture Group as a lab assistant and faculty, working in different projects and facing themes like new technologies, the production strategies, and design in through the academic and the practicing architecture. Well, but at this moment, thinking in a workshop, and working with the students, we started placing few statements, few ideas around the work. Well, so nowadays, in the middle of this pandemic that we all know, and we are in fact a little bit boring already, heard reading a few weeks ago an article in the New York Times. One student said that I'm often anxious that I will not able to join and maintain access to online classes and assignments, right? So some students have discovered that they enjoy getting to work at their own spaces. Some others are very frustrated and worrying about struggling even with this kind of learning system, right? And working now in university, we are wondering how to set up this distance learning concept. Secondly, we are nowadays living in a rapidly increasing number of interconnected devices and systems that brings both benefits and concerns, right? So this is from Sanjay Sharma. I was recently listening the lecture this last week in IAAC, the Future Learning from Sanjay Sharma. Areti Marco Polo, director, and Sanjay mentioned a few questions about how to change, or we are changing the what by the how to learn, right? So here nowadays that we can have all the devices connected through internet, how can we take benefits of these interconnections in order to set up this methodology, this pedagogical methodology that that I mentioned before. Secondly, or thirdly, maybe, nowadays in the architecture methodology or the traditional school, the way to do it, delivering a lecture on a theme and running exercise with the students, no, is maybe the most common pedagogical method, right? But is it efficient, or does it make sense nowadays to continue with this methodology where maybe students are frustrated through the online sessions? Well, Donald Sham, urban planner and philosopher from the MIT, introducing the reflection in action concept, where reflective practice is a dialogue of thinking and doing through which I become more skillful. Our bias toward thinking blind us to the non-logical processes which are only present in effective practice. And last, how the human settlements are nowadays important, were always important, but nowadays more with all these climate problematics, right? Reading this statement or this article or point, goal number 11 from the United Nations Conference report of the second committee in 2016. Make cities and human settlements inclusive, safe, resilient, and sustainable. So we can set up that implicated technology development could be, it's a goal nowadays. So, as I said at the beginning, today I'm mentioning, or I'm explaining you the work that we developed in the last Global Summer School 2020 online intense 1 week session from the 20th to the 24th, developed in IAAC. This is a work developed first with my colleague Kuna Chadda, and you can see here the important all the team in behalf of this work with the students from all different places. So from California, Dubai, but also Asia, Tokyo, Roma, Cambridge, Singapore, India, France, Greece. So working through or working towards with students from different places nowadays. The research statement during this workshop, we established a model will focus on manufacturing driving design approach towards conceiving spaces. And more important, propose it to explore a series of digital design methodologies, including the physics and robotic simulations, to explore the potential of optimization for physical robotic fabrication through remote control the robots in the IAAC place. But first, before entering or before explaining you all the work in the Global Summer School, kind of state of the art or a few works that were developed before this workshop and were really important towards the work that we finally developed. This is a seminar developed in the Master in Advanced Architecture in IAAC in the second year from Kuna Chadda, Alexander Dubor, and Angel Munoz. They were working with the students, working with new scanning technologies, human interfaces, devices, motion tracking through different plugins such as Python, Grasshopper, OpenCV, through Machina Bridge and ABB Robot Studio, and others, to through remote control the machines where the let's say the robot was a mediating device in a feedback loop which engages simultaneously the digital and the physical world. After this first seminar, also in the FabLab Barcelona, the Future Learning Unit team developed this 3-axis machine that was drawing in sand to work with the students remotely, developing different drawings and different work from where the faculty was connected with the students through the internet connection and remotely working. And now the Global Summer School. So in the Global Summer School, first, we started with the material. So the wood is one of the most widely used materials for building and construction, right? Which makes it doomed to wastage. Here you can see a few diagrams that show all these waste wood numbers that place considerable opportunities to recycle, and through these recycling processes, reuse wood material. We selected wood as material, reusing few sticks that we had already in the lab, and through already very known process that allow us to reorganize and reconfigure this surplus material environment into a reusable and usable raw material, requiring a flexible design protocol that will allow us later the industrial robots. So this demands a robot setup of continuously adaptive and iterative systems. These robots, we were working with 2 robots in IAAC, one ABB 140 and one ABB 120, that allow this flexibility to manipulate and assemble the stock to create usable, sustainable structures. From the beginning, I'm talking about this methodology that we were working with, taking in mind the pick and place process. We place on the table the digital and the physical or the fabrication parts, trying to place all these different parts and aims to decouple the digital and the physical work through a circular methodology where we could create this closed loop from design, the geometry analysis, taking in mind the physics, later also the simulation in robotics through the remote control with the machines, observing how this was working and learning, and coming back to the loop design and feeding this design and continue. This was more or less the digital workflow that we developed. So as I said, in the design part, working with Grasshopper, with physics plugin and robots plugin. I will mention later the authors. Through the Machina bridge, we send the work to the students. We're remotely controlling the machines in the lab, assembling and fabricating the structures. And we're also watching through IP cameras the fabrication and coming back to the design, going through this loop, this circular methodology, feeding and empowering the final design and final outcomes. As you can see here in this diagram, from home, through the Machina bridge, video streaming, the robot work, to the IAAC network. Students started developing different geometries by pick and place. Some of the geometries that you can see here that they were working with. Later, we evaluate this geometry through the inclination analysis of the position of each of these sticks, and finally in physics analysis with this physics plugin from Agenting Chunkao, Longuyen, and the SM coders, we were analyzing the physics and extracting information. Also, students working with the robotic simulation, and as you can see here in this video, comparing the robotic simulation with the physics analysis, extracting initially first in the digital, initially first results and first conclusions about how these geometries could perform later in the robotic process. As you can see here in this video, the physics was telling us some interesting results. Finally, at the same time, students were starting sending these files through Machina bridge plugin. Special thanks to Jose Luis Garcia del Castillo, founder and creator of the Machina bridge, with whom we were working, and already my colleagues were working in the seminar initially developed in IAAC. Here you can see a file from Abu Dhabi that was we were reaching here in the ABB 120 in Barcelona through Máquina Bridge, fabricating the spatial structure. Through this remote fabrication, students were could see final results, failure in the robotic assembling, but also could achieve some of the successful fabrication, as you can see in this specific fabrication, that thanks to the physics, they could analyze some really interesting benefits. And as you can see later in the final real physical fabrication, the outcome geometry was really interesting and was totally different than the was not totally different, but a little bit different than the initial design. Here, I would like to show you some pictures from the work. Some pictures, the works developed from the students. Where students were digital plus physical operations outcomes. Next, through this remote control, we were thinking already, or we placed on the table, how this remote control of the machines could be adapted in our current architectural pedagogical environment. And even further, can we envision an on-site construction system through remote control of the machines? I would like to finish here with this video. As you can see, this is an ongoing research in behalf of all the team in IAAC and a lot of colleagues. Thank you very much, and looking forward to discussion and share with you all this. Thanks.
Thank you very much, Ricardo. It was really interesting, and it's really interesting that you mentioned the educational model that you are adapting in IAAC. I'm sure that we're going to come back to this and also discuss the details of the project. It was really interesting. To catch up with time, we directly move to the next presentation by Yijiang Huang from MIT, Massachusetts Institute of Technology. And we ask him to share his screen. Yijiang is a PhD in Digital Structures Research Group, led by Professor Kathleen Muller at MIT. His research involves integrating combinatorial construction-related constraints into the continuous computational design scheme. He holds a Master of Science degree in Building Technology from MIT and a Bachelor of Science in Mathematics from the University of Science and Technology of China. Yijiang, you may start. Thank you. I think you're mute.
Yeah, I hide my Zoom panel and then I can't unmute myself. Now it's okay. All right. Thank you.
Have the. Oh, it's fine now.
Yep. Great. Thanks for the invitation. Today, I'm thrilled to be here to share with you about my research on scalable planning for automatic robotic spatial extrusion. So before I dive in the content of my talk, let me talk about my group and myself a little bit more. So I'm a third-year PhD student at the Digital Structure Research Group at MIT, headed by Professor Caitlin Mueller. We're a group of architects, structural engineers, computer scientists, mathematicians, and all of our research united under the one idea that we all believe performance can play a role in creative design if we use digital tools in creative ways. And for myself personally, I focus on the performance of fabrication. So in recent years, people have demonstrated the great potential of using industrial robots to directly construct large-scale complex 3D structure in the space. We take advantage of the robot's accuracy, great speed control, and high degree of freedom dexterity. And in this talk, we specifically focus one type of robotic assembly called robotic spatial extrusion. So basically here we mount a 3D printer's hot end at the end of the industrial robot. We're trying to directly distribute material or extrude plastic in the space. So people see this as a very exciting, new, appealing approach compared to the traditional layer-based 3D printing technology for fabricate sparse, discrete structure in the space because it's more natural to follow the direction of the material if you're fabricating a frame or a truss like this. And in the last 10 years in our community, people have demonstrated the great potential and the level of complexity of using robotic spatial extrusion for building trusses and frames like this. But if you take a step back and look at all the shapes that I'm showing in this in this page, you will see some kind of like repetitiveness or kind of like a pattern of the shape fabricated in this prior work. You can basically like find a specific type of like layering strategy in all of those shapes in which you can decompose it into layers, and then you will find some kind of zigzagging pattern within each layer. So let's take a look at how do designers currently generate toolpaths for controlling their robot to print those trusses. So this video is taken in my lab almost 4 years ago, and here we are seeing the robot is we're trying to like having the robot trying to follow this zigzagging pattern and extrude plastic here. As you can see, the robot's end effector's orientation does not really deviate that much. And we are kind of like following this kind of up and down motion. And usually we start with a block of truss like this. We find a way to decompose the structure into layers like X, Y, and Z. And in each layer, we can kind of easily trace out a pattern for the robot to follow. And then in Grasshopper, we can pull up our favorite Grasshopper tricks by connecting a massive amount of components together. And then through tools like KUKA PRC, HAW, or Machina, we can actually directly simulate and observe the robot's behavior in our favorite CAD design software, for example, Rhino and Grasshopper. So basically designers are directly programming very low level control script to drive their fabrication machines to do the job they want the machine to do. But if we take a step back and look at other more familiar digital fabrication technology, for example, the layer-based 3D printer, we don't actually just sit down there to spend 8 hours and directly write very detailed X, Y, Z acceleration, deacceleration G code to whenever you're trying to print a stormtrooper's hat for your cousin's Christmas gift, right? So what we do usually is we focus on the geometry. This is the gift that you want to give to your relatives. And we don't really care, really don't think much about this transition between your design model and the final execution machine. There are very mature software exist out there where you can basically just bake your mesh in Rhino and export it as the OBJ file and drag it into this software called Slicer, and the software will automatically produce very highly optimized machine code, which you can basically just copy and paste it into a 3D printer, and you press the start button, and then you wake up next morning and you will harvest with the shape that you really want to have, right? So for a robot, because a robot is a high degree of freedom manipulator compared to an XYZ gantry machine, this kind of machine is very powerful, but it's very, very hard to control. So my research focused on this critical missing algorithmic link to convert between your design model and the final execution on the robot. this kind of automatic planning pipeline to link your design model and the execution is needed whenever you want to go beyond this kind of like repetitive layer-based design logic. For example, if you want to print something like topology optimized trusses, or just more complicated 3D shapes with untrivial topology to achieve richer spatial experience. Their prior work in the field of extrusion planning usually focus on this kind of floating hand printing domain. Basically, to simplify the problem a little bit, the researcher only considers the end effector while trying to plan for a sequence of the motion. And as you can see very soon later in this talk, the kinematic constraint and the collision constraint between the robot and the existing printed structure is very critical for the whole planning process, and we really cannot simplify it out. So in this talk, I will briefly talk about two of our recent attempts in this direction of automated extrusion planning. So in order to print an irregular structure with an automated system, we have to answer two questions. So first one is, what is the feasible extrusion sequence for each linear element? The sequence or order, basically you have to specify which element to do first, the second and third. And also we have to think about how do we prescribe the robot's motion while satisfying the constraint. Those constraints include first the geometric constraint, which requires the robot must avoid colliding with the structure. And while printing, the robot's end effector's tip must follow the line of each single element. And usually in the planning field, we usually call this constraint motion planning. Additionally, the order in which the robot prints each element induces a sequence of partial structures, each of which must satisfy certain structure conditions. In this work, we consider the stiffness constraint of the maximal allowable deformation of the structure's node due to its self-weight. This constraint is important because if the deformation exceeds a certain tolerance as shown in the animation here, the elements printed in the future might fail to connect at the intended nodes. We compute the deformation of each node using finite element analysis of 3D frame structures, and notice that this stiffness checking process needs to be called many, potentially millions of times during the search because we have to evaluate once for each single partially assembled structure. As I've already alluded, this sequence and motion planning problem is a very complicated one to solve. Because we have both discrete decision, like the sequence or the order, as well as continuous decisions to figure out. The continuous decisions are basically the trajectory of the robot throughout each of the extrusion process. And because we are going down this very deep and branched search tree in order to find a solution, at the same time, we have to keep our eyes on this three constraints mentioned here. And this induces a very complicated problem to solve. So here I will briefly talk about the choreo planning framework, which we presented at Robotic 2018 and later published as an external journal paper at the Construction Robotics Journal. So in this work, we presented the first automated sequence and motion planning framework that allows you to basically just like give the system whatever truss you want to print, and it will automatically figure out the sequence and the motion for you. So here we're seeing the time lapse of a 3D Voronoi shape, which has about 300 elements, and the whole printing process will only take like 3 hours. And we also together with the paper also released an open source ROS-based implementation of the choreo planning system, which really try to give you back this kind of good old feeling of working with a slicer for the layer-based 3D printer, where you can just drop in whatever shape you want to print, and the planning algorithm will try to automatically figure out the sequence that's visualized here, as well as presenting you with a library of trajectory, which you can visualize and later directly export as G-code to be executed on your machine. The good thing for having such a general planning framework is that it's robot brand agnostic. No matter what's your favorite robot's color, you can basically just like plug in the URDF, the description model of the robot, and we don't have to change any lines of the code behind the planning algorithm. And also, as we all know, like all the architectural institutes around the world having their own customized end effector. And what we need for the planning is just like a collision model, which you can just directly export from your Rhino and plug into the planning framework. And also, without much change in the algorithm, we can also plan across degrees of freedom. So here is a gigantic ABB robot. We don't really have it at MIT, but I'm always happy to play with it in simulation. So what we're seeing here is that we're printing a topology optimized, simply supported beam using this 7 degree of freedom machine. And all of this was done without changing any lines of code in the planning backend. One caveat for Choreo work presented in 2018 is that we have this last bit of human guidance we need to give for the search algorithm. So for the 3D Voronoi shape, we asked the designer to kind of like decompose the structure into layers or groups, which will give a partial ordering or a hint for the search algorithm so that it can finish on time. This is pretty critical because as I have argued before, this problem is a very complicated one. And some really vanilla search strategy does not work directly. So in order to eliminate this last bit of human intervention, we push ourselves hard to think about more advanced search strategy in order to kind of like automate this whole planning process. So so here I will present our very recent work on scalable planning, extrusion planning, which is presented at the Robotic Science and System Conference earlier this year. So here is a video of a real-world fabrication time-lapse of a robot printing a Klein bottle. Printing a Klein bottle is particularly challenging because the elements overlap quite a bit, especially where there's two tubes intersecting each other. And also there isn't an obvious ordering even for a human that enables the robot to successfully perform the whole sequence of extrusions. However, using our latest algorithms, we are able to successfully plan to print a model, which has around 250 elements, and the planning is done within 10 minutes without any human guidance and intervention. This is 10 times faster than the Choreo first version presented before. So we present several probabilistically complete state space search algorithms for extrusion planning. Here, the state consists of the currently printed structure and the robot configurations. At each state, the search selects the next element to be printed, samples the end effector orientation for the extrusion, and perform constraint motion planning to find the trajectory of the robot that actually extrudes the element. And finally, we plan the transit motion to connect adjacent extrusion processes. So intuitively, the proposed algorithm can be categorized into two classes. The progression search algorithm, or the forward search, adds elements to the structure. Intuitively, you can think about this as growing a tree from ground up. We're planning by constructing the elements sequentially. On the other hand, the regression search algorithm, or backward search, remove elements from the completed states. Intuitively, you can think of it as playing this elastic version of the Jenga game, where you basically are trying to plan for assembly by disassembly. One drawback of the forward search is that it frequently encounters dead ends to decline constraint. The figure on the right visualizes the first time the forward search backtracks or basically kind of get trapped and starts to go to the previous explore alternative options when printing the base of the Klein bottle. The purple elements were printed first, the red elements are printed last, and the black elements have yet to be printed. As we can see, the long black elements in the middle of the structure can no longer be printed because the robot prematurely prints the left side of the structure. Even an improved version of the forward search that performs forward checking in order to try to detect dead ends earlier still get trapped. This is exactly the reason why in the first version of Choreo presented in 2018, we need human guidance to decompose the shape in order to help the forward search algorithm avoid being trapped. This motivated us to explore search in a different manner. Namely, we want to follow the general principle that it's advantageous to start the search from the most constrained part of the problem to the least constrained part of the problem. Okay, there we go. Notice that the collision-free configuration space of the robot decreases after each extrusion, simply because we are adding another body to the world. Thus, the collision-free configuration space is smallest and therefore more constrained at the end of the construction when all the elements have been printed. So rather than start from the empty initial state and build forward, we can start from the final state where everything is in place already and move backward in a regression search. This could be seen as deconstructing the structures to remove each element one by one. Thus, with respect to geometry, we're starting from the most constrained state of the problem and moving towards the least constrained state, which is the initial state. However, one complication is that the stiffness constraint is most active at the beginning of the construction. On the left is the dead-end state of the regression search. The black elements have yet to be printed. What happens here is that the algorithm prematurely removes the tension tie on the top of this tower, causing it to be no longer stiff. And here on the animation on the right, I'm visualizing the deformation of the structure because of the removal of the tension tie. Of course, the deformation is accelerated. Because of this, the stiffness and the geometric constraint are directly at odds at each other. So what we then wonder is, maybe we can bias the regression search to prioritize decisions that would enable the structure to maintain their stiffness properties. One thing we can do is that we can consider the elements in an order determined by heuristic, and intuitively, we might want to prioritize removing elements that are furthest from the ground first. Here's the distance from the ground correspond to the z coordinate of an element, and even the distance from the ground in the graph itself. An alternative approach is to combine forward and backward reasoning, where we can perform a forward search for a sequence of elements that satisfy the stiffness constraint, ignoring the robot and the geometric constraint entirely. And then we can use the indices of the elements of that plan as a heuristic, where elements with larger indices are removed first. This encourages the backward search to adhere to a sequence that is known to be as stiff as much as possible. We perform an experiment that involves just the stiffness constraint and found the ordering heuristic indeed greatly improved the success rate of the regression. And the stiff plan heuristic performs the best among all the three proposed heuristics. We compared our algorithms and heuristics in a benchmark of 41 extrusion instances with up to about 900 elements. And here we're seeing the animation of a sequence starting from the purple elements on the ground to the red elements on the top. We observed that the best new algorithm, the regression algorithm plus the stiffness plan heuristic, is at least 10 times faster compared to the Choreo first version without any human intervention of the planning. And here we're seeing some of the sequence result found by our algorithms. More videos and statistics can be found in my personal website and in the paper. So finally, we are dedicated to open source software. So whenever possible, we try to release our implementation for the paper. And out of the code for the first version of the Choreo and the scalable extrusion planning can be found on my personal GitHub repo. So in summary, in this work, we presented efficient algorithms for robotic spatial extrusion that are able to plan for very large structure without human intervention, while satisfying geometric and structural constraints. And we believe robotic spatial extrusion of forms with really complicated topology needs integrated sequence and motion planning. Thank you.
Well, thank you very much, Yijiang. It is absolutely interesting, and I'm sure that there are a lot of interesting questions and discussion to follow. So do stay with us. So we move to the next presentation by Ardavan Bidgoli from CMU, Carnegie Mellon University. And we ask him to share his screen. Ardavan is a PhD candidate in computational design at the School of Architecture, Carnegie Mellon University. His research is focused on intersection of design, robotics, and machine learning. And in his PhD research, he's working on the affordances of situated machine learning in creative activities and the integration of socio-physical aspects of craft in machine learning-based tool making. Ardavan, you may start.
Thank you, Sina, for the introduction. Just to double check, can you hear me and can you see my screen?
Yes, perfect.
Great. So hello, everyone. I'm Ardavan Bidgoli, and today I'm going to talk about context-based robotic tool making, a machine learning approach to tool making. In today's presentation, I will present the concept as well as the progress on an ongoing research project that I've been involved in. These efforts are focused on how we can leverage machine learning to make creative computing tools that are closely tied to their creators and their physical context of use. To do so, I will first discuss the classic paradigm of AI in toolmaking, and then I will introduce the situated approach to toolmaking and follow it with 2 projects based on the same idea. When we are looking at the AI literature from the 20th century, we see a common pattern. Researchers select a knowledge domain and conduct knowledge acquisition, quote unquote, methods to form a knowledge base and eventually develop knowledge systems. These knowledge systems serve as the backend for inference engines that can make decisions. Diana Forsyth, in her book, Studying Those Who Study Us, provided us with a clear and detailed observation of this process. The underlying assumption behind this approach is the concept of knowledge as an object that can be acquired, transferred, and embedded in things. In the process of tool making, this conception of knowledge crystallizes in the idea of skill transfer, which advocates for the process of acquiring skill from a user and embedding it in a machinic system. In this process, it totally detaches the skill from the human who practices that skill and the physical context that it happens in it. And this is called the decontextualization of the skill. But when we look at craftsmanship in its wide range of forms, it seems that we cannot just simply detach human skill and the physical context. So there might be a different approach here that would appreciate these factors. Treating skill as a situated entity might be that approach, where we look at the skill in relation to the human expert, the physical context, and all the ties that connecting them together. In the context of tool making, it might be possible to leverage machine learning to materialize a situated approach to tool making, where the tool is made based on the demonstrations, decisions, and subjective preferences of the user. In the physical context. In this scenario, we have bespoke data sets to train the machine learning models to make bespoke tools for specific user. To make this system work, we may use various machine learning models. The one that we chose are mostly based on generative models and specifically autoencoders and variational autoencoders. They might seem very similar because of the names, but technically they are 2 completely different entities. We chose them due to their simplicity, their efficiency and stability in training, and their ability to learn with smaller data sets compared with other architectures like GAN that require a huge data set to work with. We also look forward to testing the waters with reinforcement learning algorithms, especially Gale, generative adversarial imitation learning. But somehow, to be honest, it's not exactly what we are looking for, because reinforcement learning is based on simulation, and simulation means that you need to abstract everything and detach it from its physical context. So this is something that we're still thinking about and see how we can work with it. When we do tool making in robotics, sometimes we may need to go beyond unimodal machine learning. Unimodal machine learning is the scenario in which you only have one modality of data, for example, motion, pictures, or something like that. But for robotics and robotic tool making, we may actually go for a multimodal machine learning model, which usually combines motion, which is the thing that the robots are doing, and some other modalities of data like material behavior studies, images, like the one that we do a lot in architecture with GANs, drawing, graphs, video feeds, and other modes of data. With this intro to this whole concept of situated tool making with machine learning, I will present 2 use cases in which we tested the ideas of situated tool making. Before getting there, I want to mention and give a great shout out to Giulio Brugnaro. I hope I pronounced his name correctly. I'm pretty sure I messed the name, but and his work on adaptive wood carving, which was a source of inspiration for this project. And I saw it first in, I think, Acadia 2017 or 18, I'm not sure. It was in Boston. That was presented also 2 weeks ago in this Young lecture series. So the first project that I'm going to discuss is called Project Kivo. That was a research internship project at Autodesk Robotics Lab during the summer of 2019. This project was an early attempt to apply user style to robotic motion. Just a quick side story. We called the project Kivo in honor of Emmanuel Lubezki, a multi-time Academy Award winner cinematographer who is very well known for his long, uninterrupted handheld camera motion that are supernatural and everybody loves them. And for those of you who watched the Apple iPhone 12 keynote, he was the guy who made those videos with iPhone 12. Anyway, you may have seen sleek videos like this one, where the camera motions are so smooth that they feel unnatural. they are unnatural because they were made using a camera that was installed on a robot, and then they use 3D software in order to program the robot. In this case, this shot was made using Maya and Mimic plugin that's being developed by Evan Atherton and his team at team of colleagues at Autodesk Research. And you can see that the motions are super smooth. They are just like animation that you see in brand level animation productions. But we aim to go beyond smooth robotic motions, as you can see in this diagram, and study the possibility of using machine learning to learn a human-like motion style from a user's demonstration, and using that to generate new motions with desired characteristics to run on the robot. So instead of having super smooth motions, we wanted to apply a certain level of human pace and human-like motion to that one. The big idea was to collect data from the user, train the model on that one, and then send it to the robot and run it. In more details, we wanted to have the full pipeline with proper UI and finally execute the motion on a robotic arm. For the machine learning part, we used Keras, which is a high-level API on Python that can work with the TensorFlow backend, and the UI was made using Django framework with Python backend for the machine learning side and the JavaScript and HTML for the front-end side. So we assembled a couple of data collection tools, such as an over-shoulder rig, which is something really usual in cinematic productions. And then we put an iPad on that one so we could track the motions very accurately using Virtual Camera app. We also collected data from handheld motions, like the image that you see here, as well as gimbal and slider motion. So we had a wide range of samples, and we assembled them all together to form our data set. So this was one portion of our data set, not all of them. So it's like 1/5 of the data set that we collected. They are all around 500 motions each 5 seconds with more than 600 time steps on each one. 500 might be a small number for deep neural networks, for example, GANs. But for this simple autoencoder that we implemented at the end of this model, it was big enough to learn something. To train the model, we broke the data into its locations, its orientations, and starting points. And the reason was that we wanted to make sure that these data are not going to interrupt each other, because the scale and changes in each of them was different. And we applied normalization, removed outliers, usual suspects in data preparation. Then we trained the autoencoder, which basically tries to read a high dimensional signal, in this case 726 dimensions on each motion, and encode it to a lower dimension space that we call latent space. In this case, I think the latent space was 32, I guess. Then it tries to decode it and reconstruct the motions back to its 726 dimensions. And it's really important for our work, because then we could get this latent space that is of lower dimension, and we can trick the signal over there and play with it in order to draw new samples from the model. But first, we wanted to make sure that this model actually functional and it learns something. So we fed some motions to the model and tried to reconstruct them. And as you can see, it seems that they're pretty close. The original motion and its reconstruction are pretty close. If we want to look to this project from a pure machine learning standpoint, it was really hard to accept these samples in some cases, because in machine learning, you are working with numbers, exactly numbers, like 99.9 accuracy or reconstruction error. But here, we are working with some sort of like qualitative measurements. So we use all those quantitative methods of machine learning, but at the end, when we wanted to make sure this is functional, we relied on our subjective measures, and also we check them with the simulation in Maya. And these motions are acceptable. They are pertaining most of the characteristics that we were looking for. So after training the network, we can remove the first part of the model, which is called the encoder, and start playing with the vectors in the latent space. And we can actually trick it, add some extra noise to it, and get something different. And as you can see, the motion at the end is going to be different, and it's a new one that's being generated. So the model was working. We wrapped it up with a UI, so the user could actually visualize all the motions that it had generated and trained over, and then select the ones that it wants, try to interpolate them, try to work with them, and then send it to Maya in order to inspect and see if this is something that they are looking for. The last step of this project was to run this project on a robot and see what's going on. Unfortunately, the time frame was really tight, and it was the end of the internship, so we postponed it for the spring, and the spring pandemic hit, so we didn't have access to the robots to do anything on this side. But the theory and the model was working. We just need to test it once we have access back to these robots. And a great shout out to Evan Adderton and the people in the Autodesk Robotic Lab. The second project that I am going to introduce today is the robotic painting project that I worked on with my colleagues and friends here at CMU DFAB in collaboration with the School of Computer Science. There's a rich literature on robotic painting, most notably the Harold Cohen's Aaron, all the way to the recent entries into robotic art competition. If you haven't seen that one, you should definitely have a look. However, a main shortcoming of these projects is the lack of diversity in brush strokes. They usually rely on a very, very limited selection of strokes to create these paintings. Like they just make a motion like this, make it longer, slightly rotated, and that's it. So in the project, we decided to experiment with brush strokes and see if we can break down a painting to brush strokes and then paint it based on one person's style, based on its demonstrations. Our recipe was quite similar to the previous one with one extra step. We collected the data, we trained the model and generated new samples and tested. The extra step was a stroke-based renderer that I will discuss later in the presentation. So we drew over 700 brush strokes, again, 700 for, again, it's small, but for this variational autoencoder and this practice, it was big enough. We tried to use the real tools and materials as much as possible and limit the level of modification. So we use real brush, we use acrylic color, the paper, everything is like the one that the artist was using. And at the end, we had a data set of 2 data modalities. They were tied together, pair of pictures of each brush, and then the motion of the brush. So we had this data set with 3D elements of that one. So we also applied all those usual suspects of data preparation, like removing outliers and cleaning everything. So we wanted to test and see if our data set is clean, nice, and accurate. So we actually ran it on the robot, one of the recordings, and we test if people can distinguish between the one that the human drew and the one that the robot recreated and replayed. We actually conducted a survey. Over 100 people actually look at these 2 images and try to decide which one is made by the robot and which one by the user. The equal number of people said the top and the bottom, but actually the correct answer is the top one. And I always need to check the GIF to make sure that I'm answering this correctly. And then we started to test with different architecture of variational autoencoders, which is a more advanced model compared to autoencoders. And we developed this CNN VAE, which was later proved to be an overkill, but and we came up with simpler solutions like basically a simple VAE with multi-layer perceptron. And here you can see that we are navigating the latent space of that model trained on the brush strokes. And you can see in this GIF around 27,000 examples, and most of them are acceptable samples, but you can see that in some corners, when we go to the extreme levels, it gives us some outliers. But we actually test this one also through a survey. We asked people, we showed people a group of these brush strokes and the original ones, and ask people if you think that the model actually pertained the characteristics of the brush strokes. More than half actually told us it's doing the job correctly. But it wasn't the final goal of this project. We wanted to learn these brush strokes in order to paint the picture. But first we needed to break down the image into a series of strokes. So we picked the learning to paint model, which is a reinforcement learning based model that converts an image into a series of brush strokes. And we modified that one, fine-tuned it to make sure it's working well with our model of robotic painting. And we modified the model correctly, and we tried to convert this portrait of Maison Ling, a fictional reporter from the paper I cited below, into the sequence of dull strokes. And we tested to see if this approach is functional, and it was. In our survey, we showed this picture that was drawn by this robot with this algorithm, and 42% of people could not distinguish it as an artifact made by a robot. But this is the progress so far in this project. But the next step, which is really important for us, is to actually work with a multimodal machine learning that can actually read the motions from one side and the brush strokes that made by that motion on the other side, and try to learn these 2 models of data. So this way we can go from the motion to see what will happen if we have this motion on the robot with the brush installed, and what would be the brush strokes that are resulted from it. Or on the other side, we can actually fit the system with this brush stroke that we get from that learning to paint model, and then fit it to the model and see what would be the corresponding motion, so we can generate brush strokes in this style of the artist. So this is the part that we are right now working on, and we are looking forward to make some reports on this one later on. There are several challenges related to this situated approach. First, we need to tailor the data collection procedure to the artist. So which is really hard every time you need to do it. And we need to make a proper UI UX to make sure that the user can engage with the system. Also another challenge, because in many cases, our audiences are artists who are not expert in machine learning or computational design. On top of this, the current state of the pandemic took it toll from our research by limiting our ability to collect data, especially with respect to safety and logistics. And privacy is always a concern when you're collecting data, and we are trying our best to keep the privacy of the users and works. So this is the report on this one. Thank you very much for your time. You can have a closer look at my projects on my website. You can also check the code for these ones on my GitHub page. And we just recently at Carnegie started a research group called Cradle, which is focused on creative AI and design. And you can find all the papers that a PhD student in CMU computational design research lab are working on regarding machine learning, AI, and its new fields. Thank you very much.
Great work, Ardavan.
Thanks.
I'm sure that we are going to come back to this amazing work. We move to the last presentation by Anton. If she can start sharing her screen. Anton is from ETH Zurich. She's a PhD researcher at the Chair of Digital Building Technologies, DBT, at the Department of Architecture, ETH Zurich, where she leads the research in concrete 3D printing. She received her master's architectural degree with a cum laude in TU Delft in 2014 and continued her research until 2016 as a part of Hyperbody Research Group. Her current thesis, Tectonics of Concrete Printed Architecture, focuses on robotic concrete extrusion processes for large-scale building components. Anna, you may start.
Yes, hello, do you hear me? Do you see my screen?
Yes,
all good.
Very well.
Thank you, Sina, for the kind introduction. It is great to be here, and thank you, Digital Futures, for having me here today. I will talk about my PhD research, Tectonics of Concrete Printed Architecture, which is part of a larger aim of upscaling digital fabrication processes for architectural applications. We all know that Portland cement is a very common material, and since its invention in the 19th century, it increased in innovation, material processing, and structural applications in such a way that today concrete is the most used artificial and engineered material in the world. It is used to such an extent that it is also one of the major CO2 producers of the construction industry. However, it is not the embedded CO2 per volume unit that creates this global impact. It is rather the vast amounts of concrete we use. It is also one of the major creators of this uniform images of our cities, because we actually pour concrete in pre-designed molds that are serialized and without any customization. In a way, digital concrete attempts to break this status quo and create projects that take advantage of customization. I have selected here some digital fabrication processes for the realization of formworks. Here, for instance, we have hot wire cutting or milled foam, or robotically held in place fabrics, knitted stay in place thin formworks, and also 3D printed formworks. So all these shapes take advantage of customization and material optimization, and show that concrete can embody a new architectural expression. And now I will go to the moldless shaping of concrete, which is a research stream within our National Center of Competence in Research, Digital Fabrication. And it includes projects like mesh mold, eggshell, or 3D concrete printing, which aim to eliminate the need of traditional formwork for the construction sector. It also aims to combine the ecological advantages of no waste construction and the shape customization that comes with digital fabrication. And in a way, this shapes the focus from formal production in research to ways of controlling material properties of fresh concrete as it transitions to a hard cured concrete. So in this context, 3D printing with concrete emerges as a new technology offering unrivaled efficiency and novel customization possibilities, especially because no formwork is required. So you really have to design the robotic path and create hollow features and optimized shapes for these concrete elements. So the basic requirements for a printing system is that the material has to be fluid enough so that it reaches the placing, the tool placement, and then the material should hold its shape while coming out of the printing tool. Of course, the material that is in the layers below has to be strong enough to carry the weight that comes on top. And of course, this process should be stable enough and repeatable in similar conditions. This brings me to the point of introducing the 3D printing system developed at ETH Zurich. We all know that the notions of experiment, precision, and failure are part of the scientific method of investigation. But inside our amazing team of designers, material scientists, engineers, and roboticists, we share all these searches in a very honest way, and I wanted to capture this in my presentation. I show this failure as a precursor to the breakthrough moment where everything works, and it works especially because of this combined effort. Now the extrusion process we have developed at ETH is based on a set-on-demand printing process, which means basically that we have two components that are mixed in the extruder tool: a base mortar, Portland cement-based mortar, and the calcium aluminate activator paste. Material starts hardening immediately after it is placed on the print path, and the robotic motion is streamed online from the computer. This allows, on one hand, to capture the process parameters online and react to it, but also to transfer big amounts of data from the controller unit. This amount of data is very useful when you try to print large objects at a very high resolution. Yes, this set-on-demand process allows a very fast strength increase of the concrete, as you can see here in the red graph, how the yield stress increases very fast. But what is perhaps different to our printing process is that we use a very soft and ductile filament that has a very fast strength buildup. This filament ensures, on one hand, a very good layer bonding, on the other, a lot of flexibility in choosing the printing parameters. So we started to determine these printing parameters by small tests and experiments that try to map out the design space enabled by our technology. We look at how the print path can be designed, what are the best overhangs for our material system, and we have determined that at present we have a 30 degrees overhang. We can also vary the layer height based on flow rate, but also robot speed. This is an interesting design approach because it breaks in a way the layering effect that contour crafting usually has. What is also very particular to the 3D printing technology is that these structures have interior interior cavities that on one hand support the structure while being printed, but on the other hand they can embed additional functionality. And here we kind of decided on all the printing parameters, like what is the best layer height and layer width, what is the vertical build-up rate, because we have a very fast vertical build-up rate, we can also print very fast. However, the machines or the robots that we use cannot drive on any type of print path at the same speed. So this the design of the print path is important. Then we know that we can print self-intersecting print paths, and they actually result in better printed quality. We have the advantage of including interior structures that offer stability during printing, but also can embed additional functionality. And we know also the layer maximum layer overhang. So consequently, these geometric parameters were integrated in geometric generative engines. And for this reason, we proposed trigonometric functions and mesh subdivision as I earlier mentioned, as a way to explore this design space and figure out what kind of shapes are suitable for our technology. With this in mind, we also developed a small applet that transforms a generic computational mesh of a given height and diameter into a 3D printable column in this case. This tool also holds information about face inclination or other design tools that enable printability. And as an output of the design mesh of the design tool, we have an object mesh that is imported into the fabrication software. The toolpath is generated through slicing and place, and then the data is passed on to the robotic communication, which is implemented in Compass Fab, an open source design tool that is used for our robotic fabrication lab. It is based on the Compass core library, and the software, which is developed interdisciplinary, also as part of our NCCR, and you can of course access it online. This software was developed as part of a design studio that I led for the Master of Advanced Studies in Architecture and Digital Fabrication at ETH Zurich. This project was called Concrete Choreography, and students were introduced to the design tool, which they explored and they further developed with additional functionalities in order to design the 9 2.7 meter tall columns, which served as stage and set for the Origin Festival of Culture of last year. This is the final result of the students' work. And here I have a short movie showing the fabrication within our fabrication lab, the design tool, the final version of the design tool, and how it looked, the printing, checking out the print path, and of course of the of course, the fabrication. We have a very open approach to our research, so we were able to share all the most recent developments with our student and make and explore what we can do with them. This is the result of 10 weeks very intensive work. We also designed a mesh subdivision column that tested in a way the limits of our fabrication process. It has a height of 3.1 meters, and it was printed in a continuous process that lasted less than 2 hours. And if we look at what the digital fabrication enables, we see a large variety of column typologies that have their own sectional profiles with hollow internal structures that can be reinforced in different ways, either as lost formwork, as you saw in the concrete choreography columns, or using post-tensioning or other approaches. What is important is that in a design approach where shape tries to become efficient or as efficient as possible, we also have to match the design principles to how the shape works and how such structures can be materialized at architectural scale. Now I want to get back to this slide and show and talk about the properties of our concrete filament. As I said earlier, we can control the initial yield strength through the amount of activator with those online. So in a way, we can make this transition from concrete casting of a very fluid mix to 3D concrete printing. Now I will talk about fast complexity, which is a project developed together with my colleagues Andrei Jipa and also Lex Reiter, where we collaborated on the material development. In this project, we took advantage of how we can vary the properties of the material from their viscosity and create optimized slab elements that are fabricated using 2 different additive manufacturing processes: binder-jetting, the 3D printed formworks for the soffit, and concrete 3D printing. This approach takes advantage of what each of these 2 technologies is best at. On one hand, the 3D printed formwork has a very high resolution, and it was used for creating the visible surfaces of the slab. On the other hand, concrete printing is very fast, and it can produce optimized passes, it was used to create the absent structure, which was not visible, and it could be printed at a rougher resolution. Maybe it is also important to say why develop a digital fabrication method for slabs. It's because they represent up to 85% of the weight and cost of multi-story concrete structures, which becomes important if we think of the scale at which concrete is applied in constructions. So fast complexity is suitable for fabricating large slabs in discrete segments. The formwork of the soffit can be either used or customized for corner conditions, as well as the absent structure that is 3D printed on top of this formwork can be customized to include hollow voids for ducts, or again, a different height of the ribs for different structural applications. This is one of the fabricated modules. In our case, it's a one square meter slab segment with the beams being intersected in the middle. The fabrication steps start by firstly printing the 2 layers of a very fluid, self-compacting concrete that perfectly fill all the articulations of the 3D printed formwork. And once an initial layer of concrete has been uniformly distributed on the binder jetted support, we can stop the process or pause the process and insert post-tensioning cables or tubes for placeholders for post-tensioning cables. Then we can add the carbon fiber reinforcement mesh without needing actually any intermediate supports to place it exactly where it should be placed. Subsequently, we print very fast the abstent structure of the 3D printed ribs in a rough but very fast and efficient production way. Also, the surface quality took a bit of time to fine-tune, but eventually we managed it in a way to achieve a good surface quality. We have to take care about how we design the print path on top of the formwork, but also on the viscosity of concrete. Here you see the resulting prototype, which includes 2 segments, in total 2 square meters of a slab demonstrator. The 2 parts were assembled using a post-tensioning tendon, and then the ribs were connected with the mortar on top. I am at the final slide of my presentation, and I want to conclude by saying that this research in a way enabled the fabrication of concrete columns without using any formwork in a quite competitive time frame of 2 hours in less than 2 hours for a 3-meter tall column. But also we have developed building system for ribbed slabs that take advantage of 2 different additive manufacturing processes. In this context, I want to conclude by saying that 3D printing can also be extended to other building components, in a way taking advantage of geometry complexity, but full customization and shape variation. And all these steps contribute to our vision in which we see structural and non-structural building components being directly 3D printed with optimized material use and spectacular designs at no additional extra cost. I would like to thank all my colleagues and collaborators for fruitful collaboration, and I look forward to a discussion. Thank you very much.
Great work, Anna. Beautiful, really beautiful. So with this last presentation, we open up the panel discussion. So we ask everyone to turn on their camera. I'm sure there are a lot of interesting discussions and questions coming from the audience and also internally. And feel free to also ask questions from other presenters. So maybe we take the first question. Who wants to start?
Yeah,
first?
can I ask? I've actually got 2 questions, one for Rasha and one for Anna. But maybe I can start with Anna. We had a presentation, actually, Digital Futures, I think 2 years ago, 1 year ago, I forget now, by some of the students who worked on those columns with you. And there was a big debate about structure, And the students said, oh, we were told not to worry about structure. And they were just simply kind of reinforcing inside the columns, and it wasn't an issue. Now, I want to ask that question, to what extent, because I mean, there is a kind of certain tectonic logic that's you're following in terms of the layered concrete construction, which I think is super interesting, because I worked with Ricardo on contour crafting for a while, and I was trying to persuade him to do that. So the question really is kind of like, to what extent do those columns rely on the reinforcement on the inside, and to what extent is the tectonic logic of the layering giving it a structural stability?
Oh, okay, a very, very interesting question. Thank you. For these columns, maybe the structural aspects were not fully considered because they were part of an artistic installation, and there were other design criteria that became more important at that point. And the column in itself was solved as a stay-in-place formwork, perfectly attached to its foundation. And because it was part of a public exhibition, we had to fulfill some certain standards. However, the columns themselves were not really optimized structurally, also because they were not part of a structural system. They didn't carry anything on top, and they served only as a showcase of what the technology can do in terms of freedom of shape and explorations of these aesthetics, which for a new technology is very important to know where are the limits, what can we build with it, and what are the aesthetics that come with it.
So effectively, it's almost like a form of shuttering, right? Because that's kind of strange, because Baroque was, the whole point about photography was not to have shuttering, to build without shuttering, but then you're making the shuttering and then you're putting the reinforcement inside. Yeah. Okay. Thank you. I've got another question for Rasha, but I'll let someone else take over first.
Okay, great. So we have some questions from audience asking questions from Yijiang by Sujay Kumaraj asking, how does the robot account for any real-time deflection, if any, caused by any external factors while printing that might result in change of position in simulation versus space? I think that's a very interesting question, how we can sort of intervene the process.
That is a great question. So now I only work on offline planning because I see that as the first step towards, including any like closed loop online monitoring of the whole process. So what I envision this whole thing work together is that we can just like offline plan everything, like plan a sequence in advance. And this gave us a base. And then based on the online sensoring feedback, we can like operate on this sequence on the already computed plan, and encounter to basically just react to whatever we are monitoring on the online. And if needed, if the whole thing is really messed up, we might need to call the planner again and recompute the whole thing. And this all can be done, but now we're focusing on this like offline planning, and we haven't done anything related to like sensoring and feedback loop. But this is a very interesting direction.
Okay, if it's fine, I'm going to follow up with a question from Ricardo.
Yeah, sure. Go on.
Actually, that was also my question about the real-time feedback loop, and we know that simulation offline is one story, and then having it in real time with the robot is like totally different monster. And I'm looking forward to see how you are going to handle that part. And my question from Ricardo is about some sort of like security and safety of accessing the robot remotely. So for example, here in DFAB at Carnegie, we have 4 different robots. One of them is installed, is equipped with a plasma cutter. And if somebody get to the system from outside without proper security, that's going to be a serious issue. I want to know, like, how do you manage for these security concerns when you are networking with the robots from far distance?
Well, here in this case, we were initially checking in the simulation. I mean, that was always sure that from the simulation the robotics were working well, and finally we were sending the files remotely. So initially from the robotic simulation.
So you don't have like real-time communication between a hot robot and the user who is located somewhere else geologically?
In this case, in the workshop, was not a real time. We firstly initially we robotic simulated the work, and finally when we were sure that all was perfectly done, students were sending perfectly the files.
Okay, thank you.
Great. Antonio, you want to?
Yeah. Well, first of all, thanks everyone, because all the presentations today are really, really interesting. And especially, I wanted to ask a question to Ardavan, partly related to this issue of the feedback loop between the robot and the machine and the computer, but somehow also regarding this space of discrepancy between the motion and the way the tools are operated by the computer and humans. This is something that was touched before also on a presentation about timber chinseling, where like similar to the painting learning that you have presented, they had studied human use of chisel tools in order to reproduce a softer approach more appropriate to the timber, no? But what I found extremely fascinating is when you have explained both in the camera and in the painting how you know, the machine learning from human movement has a certain amount of noise, or if you want, a certain amount of a deviation from a smooth trajectory, and that the machine then kind of replicates that, but without the full extent of the noise, if I understand correctly. And up to a certain point you were mentioning, then there's a feedback where it kind of keeps on going back and forth between these two types of trajectory, the kind of mathematical trajectory, then the real one, and the interpolation of all of them. Yeah, so, I just wanted to ask you more about, I mean, to elaborate a little bit more about this,
sure.
This gap.
So there's a challenge here. Like, there are discrepancies between what you do as a human being with all the feedback systems that you have in your eyes, your hands, and all the senses that you have. And then we have these dumb robots that have no idea what's going on. They just follow the path unless you implement some sensory system to them. In none of these two projects, we had sensory feedback loop. But here's the point. When we are working with that camera system, we intentionally chose a system that was less problematic if you have certain level of error. When you have a camera and you keep a safe distance from the object, that's going to be fine. Despite the fact that that camera itself was more expensive than the robot, it was one of those ironies. But in that case, we were fine with like a certain level of error and the robotic motion. And to be honest, we actually applied some signal processing when we collected the data to make sure they are smooth. We removed some of the jitterings from the signal that we were receiving. If you remember from the first project that I discussed, Pivo, we were collecting the data from an iPad motion. So it was a internal accelerometer of the iPad that was sending us the data, and it has inherently some errors to it, jittering, and kind of messy, noisy data. So we had to apply some mathematical methods to clean that jittery data. At the very same time, make sure that we are not going to overkill it and destroying all the hand, shaking and other stuff. So we kept the characteristics. And when we trained the model, we also applied the mathematical method to make sure that the outputs are smooth enough, but at the very same time acceptable from the point of view of the characteristics. When it came to the painting, this whole story is different. It's very similar to the way that a couple of weeks ago is being discussed about chisel and wood. In such cases, if you make a couple of centimeters of error, it means that you're going to break your tool. So you need to be way more accurate and more careful. To be honest, painting is more merciful in this case. It's forgiving in this case, because it's, if you push your brush for a couple of extra millimeters, the brush is going to bend over, like the hair on the brush is going to move over, and you're not going to physically damage anything. But at the very same time, it's really essential to train the model correctly and make sure everything is working. And the reason that we went into those mathematical representations rather than just working with pixels regarding the motion was the fact that pixels are messy, You can get gray, values in between them. And when you apply that into motions, sometimes it's not going to work. And we had to do a lot of extra, precautions to make sure that, for example, the motions of the robot were actually in like order of like 50 millimeters, 1,000 millimeters or something like that, but the rotations were a smaller scale. So we had to do different data processing on each part of that one. So there's a delicate data pipeline here to make sure that you keep the signal, kill the noise, and keep everything consistent from the beginning and to the end. But one of the next steps that we are going to do is to actually continue working on this system and train the model not only on the user, but also the outputs of the robot. Because like I showed you that when the robot replaces the hand gestures, it's actually pretty close to what a human being is making, was almost indistinguishable. And that gave us some confidence about not implementing the feedback loop right now. But later on, we want to actually do this. We want to feed the system with these generated motions, collect the samples, and retrain the model multiple times until we get a kind of like a cascade vanishing workflow in which we are going to generate thousands of samples using the robot while keeping the 700 samples from the user and see what will eventually happen in this workflow. But it's a totally different track of research because I'm mostly focused on my PhD on the human and human in the loop, not the robot in the loop. But it's also really interesting path to study on. I hope I answered your question.
Very interesting.
Definitely. Thanks a lot.
Welcome.
Yeah, especially that loop of the machine with itself is also
that's fascinating,
very fascinating.
And scary.
I think it is really interesting to discuss about this concept of feedback. But if we put it in the terminology of systemic thinking, I think we are discussing about two different types of feedback, in my opinion. One of them is feedback, and the other one is sort of a feed forward. And what is the difference? I think when we talk about feedback, we observe the output, right? And then adjust the process accordingly. But when we talk about feed forward, we monitor the input variation, so to say. So if you think of if you think about a system, so there's an input, output, and the process. So an example that, for instance, we see in the work of Anna, it's about observing the output and then adjusting the process. While what we, in a way, see in the work of Rasha or Ardavan, it's about like monitoring this input variation, having a large number of input, and then, to me, this is more like a feed forward. So I think there's a fundamental difference. Maybe the speakers can sort of reflect on that. Do you see any difference of that sort? Yijiang, you wanna add something? Or Ardavan, you wanna continue?
Yeah, I think it's.
Ardavan, go on. Yeah.
Sorry. So I think it's actually really interesting to see that like we should definitely distinguish between these two parts. And feedback loop is actually really essential, but we didn't integrate it in this project. But I think feed forward part is also really fascinating because we can have these loops of human feeding some information, the physical system responds and reinforces it, and then the user can actually build upon that one and make this loop of tool making as a kind of like participatory platform for a human user and the apparatus it's using, which is very similar to what people used to do in past centuries about tool making. You are going to influence your tool is going to influence yourself. And I think this conversation between the user, the expert user, and the tool is a fundamental aspect here that I'm really interested in working on. Sometimes when you're using machine learning, you're losing this connection because we download some data sets from internet, from Google image search or whatever, and then we lose all the connections on the context, which is the human, the physical context, or the cultural context. But this way, you can actually keep the system in the loop. And I'm really interested in feed-forward platforms.
I want to add up on this
or
comment on this. So in our team, we also discuss a lot about what makes sense to control with the robot. And when we developed the process for 3D printing from the beginning, we started to work interdisciplinary. So we took the strategic decisions in the beginning. And for some parts, we said that it is perhaps easier to control the material to a certain degree, so we don't have to rely on on these feedback processes to control online the through motion planning or through real-time feedback, or to cater for inaccuracies of the material real-time through the process. So I think that there are problems that can be addressed through automation, but also there are other issues that can be addressed through other directions of research. And this is why interdisciplinary collaboration is so important within our field.
Rasha, did you have something to say?
Yes, thank you, Gustavo. So basically, in the case of the project I presented earlier with the stacking, machine learning is basically taking two steps. So it's kind of like it has two manifolds. One part is dealing with kind of training, because I think that was one of the questions that came up. So one is visual training, where we are training the robot to recognize the items. And on the second part is basically to give during the simulation in Unity, we're giving different patterns that we would like the stacking process to take place based on these items that have been imported. So because it's quite complicated, but basically because there's let's say six faces for the stone, or six parts for the stone or the object, it's kind of calculating which face would best fit that stacking process, and it would take a bit until it finds the best configuration. So that's why there's a lot of failures that are taking place in the second part of the machine learned stacking. And then after that, it would export that information and the characteristics of the objects that have been selected during the stacking process, and then send it back to Grasshopper to go and find this. So it's kind of like teaching a child, like, this is what I've explained earlier. This is the apple, and then if it sees a similar apple then that fits that criteria, it would go and pick it and place it. I think I answered that question also in the chat. But yeah, it's very similar, I think, to also what Ardavan has mentioned in his amazing presentation, which I really enjoyed, because I feel that he also took it even further and more detailed in that sense. Yeah.
Could I ask Rasha a question on that? I actually, 2 years ago at the Florida International University, FIU, I had a student, Jorge Tubella, who did a very similar project to you, working with the computer science department. In fact, he presented in our AI session a few weeks ago, and he faced way more challenges than you did. So I'm surprised you had such success. I mean, first of all, but there were some differences. He was using LiDAR rather than Kinect, and Kinect seems to me a bit imprecise in terms of that thing. And I think, but I mean, correct me if I'm wrong here, I think he was using reinforcement learning rather than supervised learning. And I'm very much, I'm familiar, I guess you're familiar with the work that Mike Haley had been doing at Autodesk on training robotic arms. And it was actually an incredibly challenging process, especially the issue of tolerance, which Sina raised. And you know, the kind of, I mean, it's challenging to say the least. So I'm wondering whether, I mean, you kind of presented a very utopian case as though it works, but maybe what's the honest answer? Did it actually really work as well as you claimed it did?
It did actually work. I think, like, to better answer your question, we simplified each problem. And I think, like, connecting these multiple softwares together also helped in that sense. And like, this project was done in 2017, around 2017. There's also some plugins, like I mentioned, like with Crow, that Benjamin Philbrick had developed, also helped us with this supervised training and unsupervised training, and other Grasshopper plugins like the Connect with Ladybug. So I think it's just like simplifying this connection and build up the script to do it. I'm not saying it was easy, but it was baby steps. So it was kind of like figuring out each problem and then putting it together and see how we can connect each solution to the other. But yes, it did work. That's why I'm really interested to take this further one day and see how we can basically create a more collaborative and like kind of a farm robotic field where mobile robots are also working with bigger robots and collaborating on that part. So like you have robotic arms and then you have mobile robots bringing stones to the robotic arm and constructing a wall or any other object.
I think the problem that Jorge had was once the bricks were imperfect, it was almost impossible for the LiDAR to recognize them as bricks. I mean, so anyway, I think it's great that you guys are trying this, because I mean, this is hugely important work. So thank you. Thank you.
I just wanted to follow up. Sorry, I just want to follow up, Rasha, and I guess all the other panelists, Anna. What would happen if your research were extended to a site? Because I think that was one of the panelists that presented, and it seems as though that there is kind of a utopian clinical engineering-like environment, but as I've experienced, anything can happen on the site, including human error and accidents. So can you please maybe talk about the next evolution of your research on a building site, or maybe through an engineering paradigm on another planet, like the moon?
I mean, Gustav, I work with Baroque on the moon project. What I would say is that's the question, right? I mean, I think I think on-site is extremely challenging with the atmospheric conditions, and you're probably better off. I know that Philip Yuan Feng has a kind of prefabricated things, very kind of carefully controlled environment. But I mean, Baroque's problem in some ways was he was so paranoid about his technology, he wouldn't let anyone else use it. I mean, the idea of, on a building site with, the conditions there would have been completely absurd. And that in some ways was a real challenge, frankly, between both our project and also the European Space Agency project that Enrico Dini was involved in, is that it's got to work like 100% perfectly. And if anything goes wrong, you cannot send a technician to the moon to go and fix it. So, I mean, I think that that's the challenge. And I don't think that on-site fabrication is at all feasible. But I'll defer to the other experts on this.
Rasha or Anna, do you guys want to start?
Okay, I can start. We all know that concrete printing is very popular these days. There are many research institutes, but also private entities that invested a lot of effort in developing the technology, both on site and in prefabrication. I think that there is a distinction in these two approaches. The structures that are building in prefabrication setups tend to be more accurate and explore more complex shapes that actually result in a decrease of material consumption, which is very important considering the crisis, the ecological crisis we are facing. On the other hand, we have 3D printing with concrete on site, and the results are not so convincing yet, especially because concrete is used with the same attitude as concrete is used in construction. It is seen as a very cheap material, and it is overused in one-story constructions, one-story buildings, without activating its structural potential. And I think we should acknowledge the fact that concrete is a structural material and should be used in a smart way. And if prefabrication is the way to go, then we should develop systems that enable easy assembly of prefabricated high accuracy elements that use the material in a smart way. That's my approach to the problem.
Great. Rasha, you want to add
I think in a similar way. I mean, to be honest, I never touched anything from Mars, so I don't know how the geometry there looks like, but I'm just proposing methods. Maybe if someone in the future comes up, especially that now with technology that we have, we can be on Mars and like you can send anything to Mars and really, really fast. So I think in the future, maybe someone would come and say, we have these items and we would like to build on Mars. So I honestly, it's basically a scenario that I'm building and thinking that maybe someone in the future can collaborate on this and like take this even further. And it's not only that this workflow can work on Mars, but maybe in areas where there was like a nuclear bomb that happened, or in areas where a person or a human can't reach, maybe this could be beneficial. It might have a breaking problem. It could be that something, as Neil has mentioned, it could be something that we can't do, but maybe then you send another robot to fix that issue. So I think like it's kind of like more open to other scenarios.
For the other speakers, Ardavan, Ricardo, or Hyung, do you guys want to?
Yeah, I just wanted to add something to this discussion. I think we can think a little bit more on the ground. For example, I know Mars and Moon and everything with all the NASA competitions are really hot right now, but I think we can also think about having these robots, not exactly just the industrial robotic arms, which were the topic of this discussion today, but like other types of drones, like other types of robots and other types of platform to work in tandem with human beings on the site to augment their ability. And in such cases, we are dealing with the uncertainties of a construction site. You know that you design something, you get something like 2 feet away from it, and also the human errors, and also people just walking on the side and everything. So I think like the solution is not just adding more robots, but also thinking about a framework in these scenarios that can actually handle these scenarios like more autonomously, and then it can be improved and improved and improved in order to get the least amount of intervention required by a user. We are actually working in another project at Computational Design Lab at CMU, which we are going to report in the next couple of weeks in Acadia 2020 about this semi-autonomous platforms. But at the same time, we should be really careful about trying to make a promise about technology solving everything. For example, right now the hot topic is using machine learning to solve all these problems. And we know that machine learning is fundamentally based on probabilities and statistics. And probability means that 99.99% of the time it's going to work, and that 0.001% of the time is going to be really, really catastrophic if you're sending a $2 billion explorer into Mars. If it cannot do that job one time, it's going to be over. So I think technology is not the only answer, but we should think about the ways we can, for example, at least on the sites that we can have human beings to the system, a framework in which it appreciates and advocates the human beings' errors and interventions, plus the robotic system that is going to work on that one. So we're going to discuss it later on the Acadia. Hopefully, we'll see you again over there also.
Thank you. I actually, that leads me, sorry for interrupting, but I think, I've been wanting to open it up a little bit, and I think what you just said really resonates with that. So as an observation, I thought it was really interesting that all of your work basically shows machine learning influence, but also shows the human side of experience in interaction with material. And so the kind of learning with through trial and error. And I think it's really interesting because what you just said, machine learning is still not capable of learning from experience in the way that humans do, because it doesn't have inductive logic yet. So I think it's really interesting that, the generalizing of experience from the human is still kind of necessary. And personally, I think the human will still somehow always be involved. So that the machines and robots and will become extensions of our own intelligence. But I think I wanted to open it up to you all and ask what your overall long-term vision is. What do you think will happen to us when we work with robots in that way? I think it's a very interesting and very relevant topic. So what do you think is the future of our environment shaped by these machines?
If I can say, Can I continue maybe? Yes, well, following the, can I, Sina?
Yeah, go on.
Yes, please.
Yes, so in fact, following the question that Ardavan told me before, and more or less the final video and question that I said also, well, I mean, what we tried in IAAC with this workshop and during the last month with this remote control, it was just like a really short first steps and because in fact like mandatory, because we couldn't do another thing, no. So we the only way to work this fabrication with the students was just remotely, right? But what we observed during the workshop in this global summer was different steps that in fact the students just realized it from the digital and finally later controlling the robots. They could absorb a lot of different data that they could, for example, develop in a machine learning system or developing implementing in a real time system, like you told me, another, no. But the interesting part was that at the end, no, you said, Ardavan, that technology is not the answer, no. You said, no, the price was that technology was the answer, no. And what was the question, no? I think that nowadays, and what me personally I realized that during this global summer school was that technology could be just intermediate device that is giving us this data loop to data to put inside this loop and just develop another step inside the fabrication or inside the design, no. And at the end, what we have as an outcome and what we could implement in the construction is how to remotely control all these parts to just at the end as just intermediate device, you know. So it's finally we have that the technology was just another part, another colleague to help us doing all of this. No, was not only the final influence or the final producer. No, it was just another step. No, so we can implement in our design all this technology advancement, no? And this is something that I'm thinking that is not only really relevant and innovative in the construction side that I'm really interested on, is also important in the pedagogical methodology nowadays, no? And not because it was mandatory during the COVID, no, it's because after the COVID, what we have is that it's faster to communicate through internet or to communicate by talking than going directly in flight to United States. In my case, no, that I'm here now in Barcelona. Now it's through internet that I can totally control this thing. So why not start only working through this remote control?
Thank you.
Go on. You wanna add something, Ardavan? Okay, I think it was interesting to also see in one of our previous sessions on computational design. By the way, what is interesting in this session is that maybe one shared aspect among all presentations is the fact that you are trying to incorporate computational intelligence in a way in your project, each of them in a different way. And we had a session with Philippe Morel on computational design, and then there we were. He was referring to the fact that design research includes design experiment plus entrepreneurship, basically going beyond these very experiments that we are doing and see how these experiments or these technologies sort of connect to the society. But at the same time, I would like to argue that in our work, we sort of benefit from what I can call a kind of analytic reductionism, right? We are reducing the larger, let's say, problem into something which is tangible and sort of tackleable. We can tackle it, right? But at the same time, it doesn't mean that we are sort of ignoring the fact that, hey, we have to be able to work on site. We have to be able to address larger questions. So I think this is a kind of, I would say, a wise decision to ignore some of the intervening parameters in our research. So, and I would say, in a way, all this research that we see today are sort of complementary. But back to this idea of computational intelligence, and I would say abstraction. If we also consider abstraction as one of the key fundamentals of computational thinking, I would like to sort of make a comparison between the work that Anna is doing, which deals with material innovation and starting with the material, and what Yijiang was showing in terms of how we can use mathematical modeling, mathematics to solve printing of a complex structure. So what I can see in the work of, for instance, Anna, is that, okay, first it is started with column, because obviously column is the most vertical element in architectural design. So, and then contour crafting by nature is a very vertical process. So let's start printing column in a vertical way. And then let's go to the slab. Okay, slab is horizontal. Let's print slab horizontally. But why not, for instance, print slab vertically and then flip it? And then probably we would get a probably same efficiency in construction, but maybe in terms of material constraint and structural stability, we would not get what we want. But then what we see in the Yijiang work is that, okay, the material is obviously removed from the equation to a certain extent, and then you're working in a very three-dimensional way, and you're dealing with printing in a very three-dimensional way. So I would like to ask both of you, how do you see the role of abstraction, and how do you see the way we can sort of rethink architectural geometry in a way? Maybe I would like to start with Anna. Why didn't you, for instance, start printing the slab vertically and flip it if you are thinking of a prefabricated strategy, the way Gustavo is putting it?
Yes, thank you, Sina. It is indeed a very relevant question. I think that in general, when we think of design and computational design, we have a lot of freedom to explore the design space. But when we try to apply it to real architectural scale, to large objects, then we face challenges that we don't face in virtual. So, for instance, rotating a huge slab printed vertically would be problematic, or handling elements that are quite heavy, several tons. It's not as simple as rotating a 3D model on the screen. So so in this sense, when we face the problem of scaling up the processes we work on to real construction and to real architecture, we also have to consider some other constraints that might affect the freedom we have in design. But also, I would like to ask Yijiang if or how would his tool apply to concrete printing?
Right, this is a very nice question. I'm indeed in contact with some of your team members, and we're talking about how do we apply my planner to some of the concrete printing. So one thing I want to emphasize is that the material property of plastic is not totally abstract away from my work, because remember, we have this structural constraint when we're working on sequencing. And the Young's modulus and other material properties are hidden in those structural checking. But what's really abstracted away is the thermal process of extrusion. So we basically assume that, like, when the robot extrude from here to here, we assume it's gonna be like that. And then what we're checking is the structural property of the finished extrusion process after the extrusion process is finished. But what I didn't really talk much about in my talk is like as many of our 3D printing researcher has encountered, like when you go from here to here, the material does not really want to like follow your will, right? It will sag because like the whole solidification process. So what we did not really include that into the printing process because it's almost impossible to calibrate the simulation of the thermal extrusion process accurately. And in practice, what we do is, although geometrically the printing process will be accurate, we usually need to do a little trick. Like we know it's gonna sag in that way, like for 2 millimeter, and we kind of like move to there to basically just counterbalance the sagging process. So this also connect back to Ardavan's question on feedback loop. We believe this kind of really detailed material model should be trained and should be related to the sensoring feedback. So I think this is like the whole story will come together in that way. Like we have the offline planning. It's like you're drawing the blueprint of your the whole building, right? You first determine, okay, I want to build the first floor, the second floor, and third floor, and then you're trying to figure out like what's happening really, like how do we construct this beam, how do we construct this column? Those detailed things should come after a pretty coarse like offline plan of the whole thing, and you can do a little jiggering. And of course, sometimes if something does not go as you expect it to be, you should like call the planner again and recompute, right? And going back to how does this whole thing connect back to the computational design process, that what we are trying to work on now is like it's just like a slicer for a robot. Like we basically trying to take away as much constraint as possible from the design process. So basically now it's like you can give me whatever trust you want to print, and I can put it into my algorithm, and my algorithm will give you a yes or no answer. If yes, we're all happy and we can go to the execution. But sadly, like in reality, the answer is always no. And what we are really we're really interested in right now is how do we do diagnostic, or how do we repair the shape without really globally changing the aesthetics of the design. Maybe we can like, sometimes the planning failure really comes from the detail of some corners. Like for example, this two trusses interlocking with each other. Maybe you can delete one. Maybe you can move this node a little bit in this direction. So this design question is kind of like the feeding back after we get the forward pass going. How do we give important information back to the designer? It's a very interesting question. And for concrete printing, and for concrete printing, because like we work on the stiffness model, like the structural model assumes the material can take tension. And of course, everybody knows concrete is really not like good at that. So now, for now, there's still like a deviation between layer-based printing, which is suitable for concrete, and kind of like spatial extrusion for trusses and frames. But what we are working on now is trying to generalize the strategy for spatial extrusion and to picking and placing. Because what the main critiques that we get from practitioners is that, oh, you're working with plastic and you don't live in a house built of plastics, right? So what we're trying to do now is trying to generalize those planning strategy to picking and placing so that we can maybe like picking and placing steel bars. And one of my dream is to kind of use a robot to assemble a topology optimized beam. And if we can show that this process can be really fast and efficient, maybe we can work on like maybe some of the buildings beam we can remove some unnecessary weight from them because we can assemble a really efficient rebar cages without much like additional cost and time. And then we can try to like push it into practice. And this is where, so I'm still like in the prefabrication group.
No, but that's great, because the fact that there is a high level of abstraction and algorithmic thinking, I think the material can be replaced. And if you think of assembly by nature is also a very additive process. So I think definitely we're looking forward to see how similar line of thinking and mathematical modeling can be applied in pick and place and assembly processes. But to sort of close this session, we have, let's say, 7 minutes. I would like to sort of connect what we were discussing today to maybe our next session, which will be on Africa, but not necessarily discussing about Africa. But I would like to sort of go back to the presentation of Ricardo, where he was mentioning this GSS Global School of IAAC Architecture, Global School of Architecture, which is open to all students from all over the world. So you were next to maybe AA, you were one of the first schools which opened up your doors to the whole world, and somehow Digital Futures is somehow pushing it to the next level by considering all the workshops and talks free. So I wonder if you want to sort of connect to our next topic, which is Africa, but in general, access, having sort of bringing these technologies to some sort of remote places, which don't have access to, as Gustavo mentioned, these really clean laboratory kind of facilities. How do you see these technologies sort of proliferate and become more accessible and applicable in remote areas? Maybe I would start with Ricardo, and other presenters would also add some points before we close this session.
Yeah, well, it's really interesting to see this thing growing up, and I'm really interested in this step from Digital Future. In fact, I remember to more or less start discovering this thing a few years ago when Kilian did some name. German, I guess. Sorry, I don't remember very well. He was working in the United States. In the NATO, in the national organization, and he set up a fab lab in Jordan in a refugee camp. No. And I remember that he was talking about that how the refugee needs could be solved just giving to them the directly control of the machines, you know. But in fact, this was just like a really controversial point of view, just because how to give to these poor situations the machines, you know. This thing nowadays, it could be solved just saying that could be like a remote control. So it's not necessarily giving them directly the machine, but it could be just a way to this Internet of Things concept, no? That they can directly work without staying directly in place. No? So let's say that the physical world we can nowadays transform also with all this interconnected device concept, no? And that's something I think that most, moreover, today than other days, crucially relevant, just because of the pandemic situation. No, so I'm really wondering, and I would like to place this question on the top. No, I mean, I think it's interesting with this situation now of this Africa step. No, that this remote can be remotely control this system.
Just quickly, I wanted to follow up with Victoria's question earlier about the vision. I'm hearing different visions of how we want to implement and maybe go, and I wouldn't say control, but to empower peoples from different countries and different regions. I mean, I would, Anna and Yijiang and Ardavan, like, what are your visions to make this work based on your research?
Yeah, from a very practical sense, so we try to make our work as transparent and replicatable as possible. So we try to release our code and provide instruction for how to use them whenever possible. This is just like in a very practical sense, how do we try to help at least researchers in different countries, as long as they can have internet and they can log into GitHub and they will find our paper and our code online. So maybe they can try to like try to use the tool offline. But the only issue is that maybe like industrial robot is not as widely distributed in those countries as we might expect it to be.
Yeah, I think, sorry, I'm going to continue. So I think I totally agree with him. Like making the codes available for other people to test it, first from the academic point of view and the scholarship, it's actually a really good idea. And also in the case of machine learning, data sets are super valuable. If you have access to data set, you can just work on your computer and generate results, because to be honest, the bottleneck in many machine learning problems is the data, and democratizing data is something really valuable. Making on the point that Yijiang actually mentioned, robotic arms are actually pretty hard to have. Like not every university all around the world has the luxury of having these industrial robotic arms, let alone having multiple of them. But there is a big community of people who are making DIY robots and start working with them. And I think, for example, in the case of my research, it doesn't need the workforce of an industrial robotic arm that has like, I don't know, 250 kilograms of payload, but it can actually run on small robots as long as you have the correct IK solver and control system. So I think the combination of these DIY community of people who are making hardware DIY and then releasing the codes and make it accessible for everyone, plus the data set, is something that can empower people who might not have access to all the means of technology. And I see it from my friends back at home in Iran that sometimes they have problems with accessing even the simplest tools that you have access in the US or in Europe. And I see that just because they have access to these softwares and availability of these DIY systems, they can actually practice it in a thriving community and moving on over there. So I think it's going to be really helpful.
Also from my side, we also see a lot of value in open source information and sharing all the knowledge we have. Here, we also are in the context of very large concrete companies that develop a technology which is enclosed and not shared. We try to do exactly the opposite. We have all our materials published in our papers, and all the processing strategies we have developed also freely available. This is part of our work. Also, code-related platforms like Compass, which is developed within the NCCR, it is fully available online for everybody to access.
Great. I'm sure that there are. Yeah, go on.
Yeah, just in terms of future sessions, we've also got a session on November the 14th on space architecture, and I've invited Enrico Dini. I don't know if he can come or not, but Madhu Thangavellu, who was part of the NASA project with myself and Beroko Schnevis, is going to be there. But one of the questions I want to throw out here, because actually kind of relates to the Africa one next week. Enrico had this kind of dream of 3D printing buildings all over Africa, right? That was his dream. But we now know that actually that's not quite so straightforward. I mean, you just can't take desert sand and put it into and use it for concrete and so on. I mean, that's the big issue, I think, right now in some ways, is the fact that you take a building like the Burj Khalifa that's built in a country that's full of sand, and yet the sand had to come from Australia for that. And I guess the point that we're running out of sand, I mean, one of the big challenges, and maybe you guys can address in some ways, is whether we can be working with 3D printing using desert sand, and how you might do that, because I know that it's absolutely not straightforward. Anyway, this is something that's going to come up in the future. Thank you for your presentations today. We're great, fantastic.
Yeah, great. Thanks for the closing mark, Neil. It was great. I'm sure that we can continue, but we have to close this session. So we are happy to have you, and we stay in touch. Thank you very much.
Thank you, everyone. Thank you.
Thank you. Thank you.
Thanks, everyone.
Thank you, everyone.
Thank you, everyone. Have a good one.
Thank you, everyone. Thank you.
Thank you.